Hello and welcome. In this video we're going to explore one of Cedille's interactive tooling options, the beta reduction buffer. This beta reduction buffer is very useful when proving equations. And to open it up, there are several commands, but today we'll just focus on Control-IT, which opens it with the expected type of your selected span. Inside the beta reduction buffer we can navigate around just like in regular Cedille navigation mode, with B and N and F and P. We can also, however, do some things like Control-I-N, which will replace the selected span with its normalization. Control-I comma will go back, Control-I period will redo. You can also do Control-I-H, which does the head normal form of the selected span, or Control-I-U, which unfolds it and then stops after one unfolding. So here it just unfolded the head, but then did not substitute in the arguments for the lambdas. Subsequent Control-I-U calls would do that. Anyway, let's go back. And then we can also do things like Control-I equals, which then we put in some expression, and if it's convertible, it'll replace it. So we can say, is this equal to successor of add Cn by beta? And it is. So we're good. Now, another command we can do is Control-I-R, which rewrites the selected span with some proof. So here we want to call our recursive function, which will prove that add z for some nat n is equal to n. And you can see that if you open the context buffer here. So we'll call add z1 with n, which is bound here. And now we have 2/nat n, which 2/nat is just the identity, so this is equal to successor of n. Now to check if these two sides are equivalent, you can do Control-I-F and fill this hole with any term. Here we just want to do beta to see if they're beta equal. And it says type inhabited and shows this green bar above it to indicate this is type checking. Now to apply our proof to this hole, we can do Control-I-P, and it'll stick it right in there, and as you can see, it type checks. Now let's try a little more complicated example. So Control-I-T. Here we have some pi's first, some pi types, and we can abstract those out by using Control-I-A. And it suggests the name given or from the pi. However, here, when we try to see if this is beta equal, we get that it's inconvertible. And you can also try checking it with beta. It says type error. So we're going to need a case split on one of these variables. If we look back to the definition of add case splits on n. So our proof will probably work best if we case split on n as well. So using Control-I-C, we'll put in the scrutiny n and call the recursive function add s1. Now this opens up these two children buffers for each of the cases. This is the 0 case, and this is the successor case. So the 0 case, it can tell is already beta equal and shows the green bar. So you can close that down. Now we have one case left. So again, using Control-I-A to abstract this x, let's rename it to n. And here we have add successor of m and successor of n is equal to the successor of add m to successor of n. So our recursive function, if you recall, just proves that adding successor of m to some other nat n is equal to successor of add m to that nat n, or type/add s1, which is a subtype of nat. So we're going to need to get rid of the successor first before we can rewrite with our recursive function. And to do that, if we look in the summary buffer, we can see that there is this function we've already defined, add s2, which proves that adding some number m to the successor of another number n is equal to the successor of those two added together. So rewriting with that, we can do add s2, the successor of m. We have this here. And then we're going to need to do n, but this n is a type slash add s1, which is really just the subtype of nat. So we'll need to cast it first back to a nat. And here we get it rewritten, and this 2/nat is just the identity, so that'll normalize back to just n for this argument there. Now we have add successor of m, and we want to make sure that that equals add m of successor of n. So we want to rewrite with this same proof here, except now we just have m, not successor of m, for this first argument. And there we have it. Now we have simply add mn, and we want to prove that our successor of add mn equals this add successor of mn over here. And this is what our recursive proof proves. So if we just do add s1 of n, we can see it now they're type checking. Close this down, go back over here, and then doing control IP will print out a proof of our equation. And so here we have this, and it's all type checking correctly. And if you want to review some of the commands we've just gone over, if you hit H when in Cedille mode, it'll open up the documentation, and if you go to extra buffers and then beta reduce mode, it'll list all the commands I was just talking about, plus some others. So that's it for today. Thanks for watching, and I hope this is helpful.